students. Let's today talk about another important and interesting phenomena shown by light, and that is known as scattering of light. So let's see what is scattering of light. It is the phenomenon of spreading of light as a result of collision with particles of medium. So scattering takes place when light collides with the particles present in a medium, and as a result light gets spread. So the most important and common example of scattering of light is the blue color of the sky. We all can see the sky as blue because of the scattering of light. Similarly, you would have seen that during sunrise and during sunset, sky appears like reddish. So that's also because of the scattering of light. Now let's first understand what is scattering. So when we talk of scattering of light, it's good to talk about the Tyndall effect. Tyndall effect is an example of scattering of light by colloidal particles. So there are different types of scattering particles, scattering phenomena, but at this level we only talk about Tyndall effect. So what is Tyndall effect? It's also a scattering of light. This also happens due to collision with particles of medium. But in this case, the collision happens with colloidal particles. Now, what are these colloidal particles? Again, we got a new term. So let's first understand what are colloidal particles. So in order to understand colloidal particles, we'll first understand colloids. So what are colloids? They are actually homogeneous. Homogeneous, you have read in ninth grade, where all the substances are same throughout. And heterogeneous is the mixture where substances are separable. So colloids are actually homogeneous looking heterogeneous mixtures in which the particles are dispersed in a continuous medium. So one of the common example of colloid is milk. Even another example is blood. It appears homogeneous, but when we see through a powerful microscope, we will get able to see the particles, and the size of the particles is extremely small. It's between 10 raised power minus 9 to 10 raised power minus 7 meters. So it's not easily visible. But with the help of high power microscope, we can see those particles. So now it will be easy for us to understand Tyndall effect. So Tyndall effect is the scattering of light by colloidal particles. That areas that light spreads by extremely small particles. The color of the scattered light depends on the size of the scattering particles. Which color of light gets scattered, that depends on the size of scattering particle. If the size of scattering particle is very small, it will scatter only small wavelengths. And if the size of particles is big, it will scatter bigger wavelengths. This is very important to remember because this forms the base of all scattering phenomena which we see around us. So one of the beautiful example of Tyndall effect is you would have seen that light rays enter even inside the dense forest, right? How is that possible? That is because of the small particles which are present in the atmosphere. Light collides with those small particles and gets scattered, and that is how light enters even inside such a dense forest, and you are able to see the beam of light, that path of light. Sometimes you are say suppose you are if you are sitting inside a room and it's very sunny outside, and you have an extremely small hole on your window, and you see light rays coming through that hole. In that case, you will be able to see the exact path of light. You could see even those small particles in that beam of light. So have you observed that? This is known as Rindell effect. That is the particles present in the atmosphere. If those particles are smaller in size, they will scatter smaller wavelengths, and if the particles are bigger in size, they will scatter bigger wavelengths. If the particles are big enough, they can even scatter white light because it has got high wavelength. So it was all about Tyndall effect. Now let's see, why does the sky appear blue? Now in this case also what happens, atmospheric particles which are present are extremely small in size compared to the wavelengths of light, white light. Just now I told you that if the particles are small in size, they will scatter smaller wavelengths. Now if you look at the spectrum of white light, you would see that the red end of spectrum, that's red, orange, yellow, that end of spectrum has comparatively larger wavelengths. as compared to the blue end of spectrum, that is violet, blue, indigo. So that end of spectrum has smaller wavelengths, so therefore these small particles of atmosphere scatter smaller wavelengths, so they scatter blue end of spectrum, and the red end of spectrum is not scattered, and as a result sky appears blue, because the factor which is responsible for the blue color of sky is the small size of atmospheric particles. So suppose if there is no atmosphere present in that case, what would happen? What would be the color of sky if there is no atmosphere present? That means if there is no atmosphere, that means there is no atmospheric particles present. So there would be no particles to scatter light. And as a result, in that case, the sky would look black. There will be no color of sky at all. Now the same thing happens at the time of sunrise and sunset. You must have observed that during the sunrise and sunset, the sky, the sun appears reddish. So it's also because of the same phenomena, because of the refraction, because of the scattering of light. During sunset, at the time of sunrise and sunset, what happens? The sun and the surrounding sky appear red, because at that time most of the blue color present in sunlight has been scattered out and away from our line of sight, and leaving behind mainly red color, the one with a large wavelength, and that directly beam of light, that red color beam of light, reaches our eyes. So during sunrise and sunset, when sun is near the horizon, the sunlight has to travel the greater distance through the atmosphere to reach us. And during this long journey, most of the shorter wavelengths, blue color like, are scattered out and away from our line of sight. So the light which reaches us directly from the rising sun or setting sun consists mainly of longer wavelength, red color, due to which the sun appears red. And due to the same reason, sky surrounding the rising sun and setting sun also appears red. Thus, I hope you are now able to understand why sky appears reddish at the time of sunrise and sunset, and why sky appears blue. And same thing happens why when sun is at the overhead in the sky, and at that time sun appears white, because at that time when sun is overhead, like at noon time, then the light coming from the sun has to travel a shorter wavelength, a shorter distance through the atmosphere, and during this short journey of sunlight, only a little of blue color of white light is scattered. Most of the blue light remains in it. And now since the light coming from overhead has almost all its components, all the colors in the right proportion, therefore the sun in the sky overhead appears white to us. This was all. Thank you.